Thank you for inviting me. I'm very grateful to the organizers for doing so and for arranging the online variation. I would have much preferred to be there in person, but unfortunately, some family medical problems prevented me from traveling. So you will let me know, by the way, if you're not hearing me right at any point.
All is perfect.
Okay, this is a topic that has long interested me, and I'm going to be speaking on the importance of philosophy of science for statistical science and vice versa. You know, statistics has long been the topic of controversy that has reached high levels of personal and professional passions and controversies, and I call them the statistics wars. Statisticians, by and large, are aware of this, and sometimes they even call the philosophers in to talk about these. This is the statistician George Bernard at the beginning of his 85 book saying that confusions of the foundations of statistics is responsible for much of the misuse of statistics that we meet in medicine, psychology, sociology, economics, etc. You know, the 1980s, when he was writing, when we saw a move in philosophy of science to be relevant to practice, I think the philosophy and philosophers of statistics were sort of ahead of their time. You would see statisticians attending philosophy conferences and philosophers at their conferences, and that is actually less so now. Of course, we have formal epistemology, but that's really different. And I'm going to say we really need much more interaction. At one level, statisticians and philosophers of science ask similar questions. What should we observe, and what can we infer from the data? And how well do data confirm or test a model? How do we distinguish spurious from genuine regularities, avoiding being fooled by chance? How can we infer more accurate and reliable observations from less accurate ones? I want to emphasize, though, that statistical methods enter when effects are neither swamped by noise nor so clear-cut that no formal assessment is even needed. But when you are in this situation, you definitely want to avoid being fooled by chance. I see the fields as a two-way street. As Oscar Kempthorne says, statistics is a kind of applied philosophy of science. In one direction, statistics is a great resource for philosophy of science, for deciding how to model scientific inference, for solving or at least reconstructing philosophical problems about evidence and inference, notably the problem of induction, and for performing a meta-methodological critique, like, should we prefer novel predictions? Why? Does multiple testing matter? Things like that. In the other direction, a central job for philosophers of science is to minister to conceptual and logical problems of the sciences. This is especially so when widely used methods like statistical significance tests are said to be causing a crisis and maybe should be abandoned. Members of different schools in statistics often talk past each other, and the whole field really has its foundations more in turmoil than ever, especially with introduction of data science and machine learning and so on. Given the focus of this conference, I'm going to direct myself to the second direction largely, the role of philosophy of science in statistical science. I'll ask three basic things. What are the key debates really about, and how should we critically appraise some of the recent statistical reforms? And finally, how to reformulate and improve statistical significance tests and other controversial methods. Okay. One of the key points of controversy has long been the role of probability. Should probability enter to control the relative frequency of erroneous inferences in some series of applications, or should it enter to assign degrees of belief or support to claims? Well, the wars between frequentists and Bayesians have been so contentious that everyone wants to believe that we're long since past them. After all, we now have various unifications between subjective and objective probability, and maybe it's the end of foundations. And it almost looked that way around 15 years ago, but these unifications didn't really work out. And the bottom line is that longstanding battles still simmer below the surface in today's statistical replication crisis in science. So what's behind this drumbeat that statistical science is in a crisis? By and large, it's the fact that high-powered methods have gotten so effective at finding impressive-looking effects, even though they're due to chance. And so I tried to start with this area of controversy with something we can more or less agree on, I hope, a minimal principle of evidence, that we don't have evidence for a claim if little, if anything, has been done to rule out the ways in which the claim is false. Okay. So here's this idea then that we can view statistical inference as severe testing, that we will use probability to try to figure out how capable methods are at unearthing mistakes and errors. And even if you don't agree with this idea, one need not at all. I regard it as an excavation tool for getting beyond the statistics wars, as I say in my title, and for appraising reforms. Now, many of the reforms are welcome, like pre-registration, a protocol, replication checks, avoid cookbook statistics, but others are radical and can even make it more difficult to hold people accountable for errors and even violate the minimal requirement. Being an outsider, if a philosopher, can actually be helpful, not just because of the critical acumen, but in order to combat some of the self-defeating reforms, one finds oneself taking on strong ideological leaders, and avoiding the bandwagon can sometimes be scary for people in the field. Okay, so let's start then with the fact that the most often used tools are the most criticized. And this is John Ioannidis in this famous paper from 2005, saying that the problem leading to non-replication of research is a consequence of the ill-founded strategy of claiming conclusive research findings solely on the basis of a single study assessed by statistical significance, p less than 0.05. Well, this comes as a shock to most people who know anything about tests. Ronald Fisher, a founder of statistical significance tests, emphasized many times that we're interested not in an isolated record, but a reliable method of procedure, that in relation to a test of significance, you can only say a phenomenon is demonstrated when you know how to conduct an experiment that will rarely fail to give us statistically significant results. We're not interested in just an isolated case. Okay, so what is a simple significance test? Their goal is to test the conformity of data with some reference hypothesis, often written H0, in some respect. We find a function of the data called a test statistic, which tracks the difference between the data and this reference hypothesis, such that the larger the value of t, the more improbable the data are under H naught. And the p-value is the probability you would have gotten an even larger value of t than you observed under the assumption that the data come from a world adequately captured by H naught. Small p-values indicate some underlying discrepancy from H naught, in my view, because probably 1 minus p, you would have seen a less impressive difference were H naught true. Requiring the small p-value before saying you have some evidence of a discrepancy also ensures that you won't erroneously infer such a discrepancy. But even if you've got a small p-value, that's not evidence of a genuine statistical effect, as Fisher just told us. Yet alone is it evidence of some scientific conclusion, which we can write as H star. The error probabilities for the test don't apply automatically to some subsequent claim, although abusers of tests do commit such howlers. And this footnote here is to emphasize that I'm using the word indicate before we have an audit, which is going to require testing the assumptions, which is really part of the account. Now, Name and Pearson really put Fisherian tests on firmer ground. They introduced the alternative. Fisher only had that null. An example might be that the null hypothesis says that the mean of some distribution is 0, no effect, let's say, or some effect. And by introducing this alternative, they have the trade-off between type 1 errors, erroneously rejecting, and type 2 errors, erroneously failing to reject, and the related notion of power. And this restricts the inference to statistical alternatives in a model, so you won't fallaciously use them as readily. Okay. However, Fisher and Neyman did disagree on things. I call them the pathological battles, even though they started out very much on the same side. The bottom line is that the success of Neyman-Pearson at optimal error control led to a whole new paradigm in statistics that's still very important today, not just in statistics, but machine learning and artificial intelligence. But this formality tended to overshadow Fisher's more informal notions. And then there's the fact, as David Cox says, that the two were in the same building and they disagreed. And the fact that Neyman wouldn't use Fisher's book in his class and things like that. But it's important to see this because contemporary casualties of these pathological battles are very much with us. We hear that Neyman-Pearson and Fisherian tests are an inconsistent hybrid. This is Gerd Geigerenzer. And in this inconsistent hybrid, Fisherians presumably can't use power. Neyman-Pearson testers can't report the attained p-value, but only fixed p-values like p is less than 0.05. The truth is that they all use very explicitly both pre-data error probabilities and post-data p-values. And so it's useful to know the philosophy and the history of statistics to avoid some of today's confusions. The two accounts are essentially mathematical identically, even though their philosophy differs. They both fall under what I would call error statistical tools. These are tools for assessing and controlling the probability of seriously misleading inferences in a series of applications. And under that rubric of error statistics, I'll put confidence intervals, resampling, randomization, and others besides. And they certainly agreed in saying You know, it's easy to lie with biasing selection effects. Fisher always called this the political principle. Sufficient finagling, cherry picking, multiple testing, searching post-data subgroups, look elsewhere effects in physics may practically guarantee an impressive looking effect, even if it's unwarranted by evidence. This violates the planned error control and severity, right? So here's the requirement saying that we only have evidence for a claim to the extent it has been subjected to and passes a test that probably would have found it flawed if it is. And this probability is the stringency or severity with which it has passed the test. So we're going to use probability to evaluate the capability and thus the severity of the test. This goes beyond frequentist performance because good long-run performance, while a necessary condition for severity, is not sufficient. It's also, looking at it this way, a key to solving a central problem for frequentists who are always put on the defensive for why should good performance be relevant for a particular inference, not just for acceptance sampling in industry. Ask yourself, what bothers you with selective reporting, cherry picking, stopping when the data look good? It's really not just about long runs. It's true that here's, a data dredger or somebody fishing for significance. It's true that the person is using an unreliable method. But what bothers us is that we can't say in the case at hand that they've done a good job of avoiding the sources of misinterpreting data. They're not seriously trying, as Popper would say, to find flaws in their claim. So the goal was to try then to come up with an inferential construal of error probabilities. And this is in a paper with David Cox, so that the hypothetical error probabilities can be used for inference. Of course, there are many attempts to do just that, but all the other ones are probabilist in nature. You might wonder, by the way, how a philosopher of science wound up working with Sir David Cox. And it's interesting to note that what happened is in 2003, I invited him to be part of a session on philosophy of statistics at an Eric Lehman conference, Lehman being a student of Neyman's, and he agreed. And after that, we put some of our work together and wrote a couple of papers. So now to compare the three different uses of probability in terms of when is a claim not warranted, for what I'm calling the probabilist, it's not warranted unless the claim is true or probable or gets a probability boost made comparatively firmer or something like that. Okay. For the performance person, it's not warranted unless it stems from a method with low long-run error. And under that, we can give it another P, probativism or severe testing. It's not warranted unless something, a fair amount, has been done to probe and rule out ways we can be wrong about C. So the three Ps. Severity is Popper's term. He was right to point out that the probability of a statement doesn't express an appraisal of the severity of the test a theory has passed. And it's fascinating to see that the disagreements between Popperian falsification versus logics of induction and confirmation in philosophy very much parallel disagreements between frequentists and Bayesians in statistics. But the bottom line is that Popper never cashed out his notion adequately. He never made what I call the error statistical turn, but he could have. And actually, he wrote to me about this on a couple of occasions. As far as logics of confirmation, A good example is Ian Hacking's law of likelihood. He's a philosopher, and this is 1965. The law of likelihood says that data support hypothesis H0 less well than H1, so far as H0 is less likely in this technical sense. That is, the probability of the data under H0 is less than the probability of the data under H1. These are the two likelihoods, and likelihoods are often misunderstood. Here, it is the data that are fixed, and the hypothesis can vary. In fact, any hypothesis that perfectly fits the data is going to be maximally likely, whether it's data dredged or not. It's really a matter of the relationship between statements of the data and the hypothesis, and this fits the idea of a logic of induction. However, what happens is there always is such a rival hypothesis that you can dream up, namely that things just had to turn out the way they did. This is George Barnard again. In other words, the probability that H0 is less well supported than H1 for some H1 or other is going to be high, even if H0 is true. What I'm emphasizing here is this is an error probability that goes beyond this comparative support, right? It's one level removed, so to speak. And Neyman Pearson always said we'll use likelihood ratios, but we really can't understand if they're big or small unless we look at the probability that you would get such a value erroneously. Okay. By the time philosophers really started to notice hacking, he had already retracted this law of likelihood and even said there's no such thing as a logic of statistical inference. But his book is wonderful and, should be looked at. Anybody interested in this area. He even took back his criticisms of Neyman Pearson, saying that Neyman, Peirce, and Braithwaite were on the right tracks in the analysis of inductive arguments. Nevertheless, a pervasive view remains that is connected to his account, and that is that all of the evidence from the data are contained in this ratio of likelihood. This follows from inference by Bayes' theorem, by the way. That is, if you run inference by Bayes' theorem, then all of the data is going to come in this ratio. It's also referred to by them as the Bayes factor. Okay, and you should keep in mind that likelihood of a hypothesis is not its probability. For example, two rival hypotheses can both have maximal likelihood if they perfectly explain the data. And this principle that all the evidence is in the ratio of the likelihoods is called the likelihood principle, or the strong likelihood principle. And according to the likelihood principle, going that second level to the error probabilities is appealing to something irrelevant. And this is the subjective Bayesian Dennis Lindley saying sampling distribution, significance levels, all these depend on something more than the likelihood function, and therefore something that's irrelevant in Bayesian inference, namely the sample space, by which he means that once the data are in hand, it is irrelevant to consider what other outcomes could have occurred. Okay, and by the way, this is the same Dennis Lindley, since we've been talking physics here, that prompted an inflammatory letter regarding the 5 sigma Higgs discovery in 2012. Well, not too many people were aware of this, but he was asking, why are they using such an extreme evidence requirement? Is the particle physics community completely wedded to frequentist analysis? Anybody told them what bad science it is? Not bad science at all. The particle physicists were quite and are quite sophisticated about their statistics. And there's a group called PhiStat made up of physicists and statisticians who did not agree with him. But nevertheless, the truth is that many Bayesian reforms that we see offered as alternatives to significance tests do follow the likelihood principle. And we hear that these Bayes factors can be used in the complete absence of a sampling plan. And in a book called The Likelihood Principle by Berger and Wolpert, they say it seems strange that a frequentist couldn't analyze data if they didn't know the stopping rule, that is, the plan for when to stop sampling. Shouldn't data speak for itself, they ask. Well, no. Here's an example of the effect of repeated significance tests on the p-value. This is an example of a two-sided test of the mean of a standard normal distribution. And the probability of rejecting the null with a result that is nominally significant, let's say it reaches 2 standard errors, at or before n trials, even though the null hypothesis is true, increases and very quickly becomes high. And as a matter of fact, using this optional stopping, it can be guaranteed that you will stop and reject the sharp or point null hypothesis, even though it's true. And this is Edwards, Linman, and Savage talking about this back in 1963. Even though they admit that, they also agree that from their Bayesian standpoint, the stopping rule is irrelevant because it doesn't enter into the likelihood ratio. Contrast this with the reforms from replication research. Replication researchers, I say, rediscovered that data-dependent hypothesis and stopping are a major source of spurious significance levels. And the reason I say rediscovered is that, of course, in medicine and other fields, it was well known that you had to predesignate things like how many trials you're going to run, how many hypotheses you're going to test, and so on. But they were surprised that it had such a great effect on the probability of finding impressive-looking departures. And these are the well-known fraudbusters, Simmons, Nelson, and Simonson, who mandated that authors decide on the rule for terminating data collection at the start. But still, I find this very surprising that current Bayesians often echo the exact words of Edwards, Linman, and Savage. And this is Eric John Bonamaker's in psychology saying, yes, you'll definitely be able to stop even though the null hypothesis is true. Seems like cheating, or it might look that way, but he says, no, according to the likelihood principle, it's not. That, of course, assumes the likelihood principle. So we have a kind of replication paradox, as I call it, in today's discussions in statistics. So a critic of statistical significance tests might say, you know, the problem is it's just too easy to satisfy standard statistical significance threshold. But why is it so hard then to replicate significance threshold? Isn't that what the replication crisis is? That people are unable to get the significant result to show up again when they have more stringent protocol. Well, it must be that the initial studies were guilty of p-hacking, cherry picking, and data dredging. Oh, so you say the replication researchers clearly want methods that pick up on these biasing selection effects. Well, actually, continues the significance test critic, the reforms recommend methods where there's no need to adjust for multiplicity. This is the situation that we often have And it's not just people talking philosophical foundations, but has direct consequences in clinical trials. Trialists say they're in a quandary. These are Bayesian clinical trialists because the FDA and other regulatory people require them to control the type 1 error. But in so doing, they say we're losing their philosophical advantages, like compliance with the likelihood principle. So it's pretty interesting that this philosophical principle is one that goes against error control. And this is in exploratory studies because they're not allowed to do this in confirmatory, but they will still require that they adjust for multiple testing. This was part of a session that I was in on why do we disagree? Why do people in clinical trials disagree? Well, it's pretty clear why, if one group is holding the likelihood principle and the others demand error control. Now, probabilists can indirectly block intuitively unwarranted inferences because at least Bayesians have not just likelihoods, but also prior probabilities. And the trick is to give a high prior to that null hypothesis of no effect. Okay, if you give a high enough prior, often called a spike prior, it's still going to have a high posterior probability. But the problem with this is it doesn't show what researchers had done wrong. It becomes a battle of beliefs. The problem was the multiple testing. Really, the data-dredged hypothesis is often very believable, and that's really what makes them so seductive. Once you find them, it seems that, they've got to be right. And so it's just an additional source of flexibility. After all, the priors can also be data dependent, and it's unclear how to interpret them. In fact, most Bayesians the last 15 years resist using really subjective priors. They would rather use conventional or objective priors. When Berger came out in 2006 with his objective Bayesianism, he recognized, he said, well, scientists don't want to do a subjective analysis, and so they're not going to use Bayesian methods at all unless we change. So he was calling on the field to adopt these objective priors, which prevent prior beliefs from influencing the posteriors. They're said to be data dominant in some sense, but the question is, what sense? There has been no agreement on the rival systems for these non-subjective conventional priors, and clearly no uninformative priors, although it was hoped that one could be found at one time. Conventional priors may not even be probabilities since they're typically improper. And there are all of these different systems for obtaining these conventional priors, max and invariance, coverage matching, which will allow them to match error probabilities. Okay, but when they do match, they have to violate the likelihood principle. But so when you get some software to use a Bayesian test, you'll get some kind of default, and it won't be clear what it means, but the spike prior to the null hypothesis of no effect will be implicitly in there. And as a result, the posterior probability for the null no effect, for example, can be high even when the data are reaching a low p-value. And this, of course, is a famous result, often called the Jeffreys-Lindley paradox, but better regarded as the Bayes-Fisher disagreement. You've got this lump of prior given to the point null. It could be 0.5, but it's a lot when the remainder is spread over the alternatives, sometimes called the spike and smear. And a result that would have reached the level of small alpha can actually correspond to a high posterior probability, like 1 minus alpha. Okay, especially with large n. This problem becomes worse as n increases. For the Bayesian, the p-value is exaggerating the evidence against the null because the p-value is small, seems to indicate evidence against, but they're assigning not really so much a high prior, but too high to say you have evidence against it. So while the Bayesian sees the frequentist as exaggerating, the significance tester objects to the fact that they're taking low p-values as not only no evidence against the null, but even evidence for it. So you might have heard of one of the popular reforms because philosophers did weigh in on signing on some of these to redefine statistical significance. And this same spike and smear is the basis for the move to lower the p-value threshold to 0.005. And this, I've got only one author here, but there are quite a few who had signed on to this. There was another mega team that opposed by Lakins et al. And said, we shouldn't, but we should choose the particular p-value threshold according to the balance between type 1 and type 2. And it isn't, the problem isn't lowering the p-value. It's all a matter of what balance you want between the probability of type 1 and type 2 errors. That's not the problem. The problem is assuming there should be agreement between quantities measuring different things, and that even when the numbers are the same, they're interpreted completely differently. But I will say a silver lining to distinguishing highly probable and highly probed claims is a good one that suggests you can use different methods for different contexts. Okay. In fact, trying to reconcile methods from rival schools often creates confusion. And in a paper that I'm looking at now called A Bayesian Perspective on Severity by Van Dongen and others, they say, yes, Mayo is right. The Bayes factor is insensitive to the sampling protocol that affects error rates. Still, Bayesian can satisfy severity, they claim, regardless of whether the test has been conducted in a severe or a less severe fashion. Well, that becomes very puzzling until you realize that now they're using severity in a different way. They're talking about having one hypothesis be more likely than the other, or equivalently, that the Bayes factor can be very high for one hypothesis. This is a comparative approach. There's a very strong difference in goals. So we can take this up more in the discussion if people want. So, but I'm not saying that there isn't overlap or that Bayesians and frequentists can't use each other's methods at times. Some Bayesians do reject probabilism. An example is Andrew Gelman, who calls himself a falsificationist Bayesian. And here he is in a kind of meeting of the minds with Cosma Shalazy, who's an error statistician, who's saying, yes, at least in the sense of needing to check our models, we can add error statistical probes to our Bayesian account. And what we're advocating, they say, is what Cox and Hinckley call pure significance testing, where we've just got this model and we're testing it against the data. But then it becomes puzzling to also go along with the recent mantra to abandon statistical significance. So let me say something about the current controversy, so you don't go away without knowing something about them. At the American Statistical Association. In a nutshell, back in 2016, they put out a statement on p-values, which just rehearsed some well-known restrictions on how to interpret p-values. P-values aren't measures of effect size. They're not posteriors. They're invalidated with selection effects. And they alone shouldn't be the basis for scientific inferences, all stuff that people knew. That was a policy paper. But in 2019, surprisingly, the ASA executive director wrote an editorial just under his own name and a couple of co-authors saying the 2016 statement stopped just short of recommending that statistical significance be abandoned. And we're going to take that step here as if it's just a small step beyond what the policy document had said. And they claim whether a p-value passes any arbitrary threshold shouldn't be considered at all in interpreting data. This is the 2019 statement. Now, many claim, they hope that if you don't have the p-value threshold, researchers are going to lose the incentive to data dredge and multiple tests to try to get to that low p-value. I argue it's really the opposite. How can you hold the data dredger accountable if you're not allowed to look at thresholds for small p-values? I mean, they cannot claim that they have evidence for discrepancy with a large p-value because it wouldn't make sense. They'd be saying, even though probably to get an even larger difference than I got by chance alone, I claim I've got evidence that it's not chance. So they've got to still have a small p-value. But if you can't say about any results ahead of time that they won't be allowed to count in favor of a claim, that is, if you deny any thresholds, you don't have a test of C. We shouldn't have unthinking thresholds, but is anyone in favor of error probabilities of over 50%? You know, Neyman Pearson always had an undecidable region, so it isn't a strict dichotomy. But having seen that announcement, many researchers, or some, lost little time saying, given this call to abandon significance testing, it may be useful to move away from controlling type 1 error entirely. These were these same groups of researchers from radiation oncology. Well, useful for whom? Not for the skeptical consumer, you and I, who bears the brunt of the results here, where we really need to know how many chances they've given themselves to find something interesting before inferring the result. Typically, again, with the exploratory inquiry, you would then go on and test with new data, but they're saying, error control, we don't need it. I want to be very clear that I'm sympathetic, Barry, to moving away from accept, reject, behavioristic acceptance sampling uses of tests. I've been talking about this for decades. And in my way of reformulating tests, instead of a binary cutoff, a particular outcome is used to infer discrepancies that are or are not warranted with severity. And I've worked on this with many others, Arispanos, David Cox, David Hand. And I'll give you an idea of how you could do this with the simple case of a one-sided test where the null hypothesis would say mu is 0 or less than 0, doesn't matter, versus greater than. Well, I'm imagining the standard error here is 1, and we will reach the cutoff with 2 standard errors. That indicates some evidence that mu is greater than 0. That's the typical p-value 0.025. But that's not very informative. What other discrepancies can be ruled out and how severely. Mu greater than 1 only reaches the severity 0.84. Inferring mu greater than 2 would be poor, reaching severity only 0.5. It's important to see that in these tests, the inference is not to a point of this parameter, but to an inequality of the form, mu is at least this big or something like that, where mu1 would be the null plus some discrepancy parameter. Notice the difference between severity and power. What's power? Power is the probability the test would reject the null hypothesis, okay, under the assumption of varying different values for the alternative. And here we may imagine that we're going to reject the null if we reach the sample mean, that's X bar, of 2 standard errors or more. Well, power goes in this direction, the probability that you would reject under the assumption of these different discrepancies increases, as makes sense. But severity goes in the reverse direction. And I'm just saying that the confusion about power is, one of the greatest obstacles these days. So this opposition we see is also how severity avoids the large N problem. And really, this is what's behind the Jeffrey-Lindley paradox that I mentioned, where the p-value can be small, but the posterior not small. As you fix the p-value, if you keep it fixed and you increase the sample size, the 2 standard error cutoff is going to get smaller and smaller, so it's closer and closer to the null. And some people would say, well, you really should change your p-value as n increases, and that might be so. But even if you don't, you can correctly interpret the result. Severity tells us that a difference that's just significant at level alpha indicates less of a discrepancy from the null if it results from a larger sample size than a smaller. Here's an analogy that will show this right away. What's more indicative of a large effect? Let's say a fire with a fire alarm that goes off with burnt toast, or one that doesn't go off unless the house is fully ablaze. Typically, I would ask people to answer this. The larger sample size is like the toaster that goes off and the alarm that goes off with burnt toast. So really, it's the more coarse alarm that is more worrisome and should be scarier. Of course, we do need to have a sample size that is big enough to justify the assumptions of the statistical model. Okay, but that's the reasoning. What about the fallacies of non-significant results? This is, again, a huge problem. And we often hear that a non-significant result is completely uninformative, but that's not true. Minimally, failing to be able to find a small p-value, whatever it is, shows that the test was incapable of distinguishing the effect from noise or background variability, couldn't protect you from being fooled by chance. But you can also go further often and use severity reasoning to rule out discrepancies, as scientists often do, to figure out which theories are worth developing. In other words, we can use it to set upper bounds. If you needed to get beyond a sample mean of 2 before you reject, okay, well, you clearly can't say you have evidence that 0. You start to get more and more severe as you consider larger upper bounds. And so this also connects to confidence intervals, but improves on confidence intervals by giving an assessment to each of the points in the interval. Okay, so I'm going to close to say that most relevant way, the most relevant way philosophy can be relevant to science, deliberately talking about what's the most relevant way to be relevant, is to solve or at least illuminate logical, conceptual, and value-laden issues in the field, not just working in the subject matter of the field, although that's interesting too. And I discussed 3 philosophical tasks: elucidating the core controversies. It has to do with the nature of evidence and the role of probability. Are you going to use probability for error probabilities or not? Second, critically appraising the reforms. And third, reformulating statistical significance tests. I haven't discussed 2 crucially important other ones that I've worked on, namely linking statistical inference to substantive scientific claims and testing statistical assumptions, part of auditing. Thank you so much for listening, and I would be very glad to have your questions.
Questions? There are no questions here.
I do have a question.
Go.
Yeah. First of all, let me begin by thanking Professor Mayo for the very enlightening talk. I would like, however, to hear more about the severity measure and the idea that it's one level removed from in terms of assessing evidence. I think that it's when you are later presenting it using the graphs and so on, it was not clear to me in what sense it's one level removed, if you're talking about the parameters involved in
any method that you use, okay, you give me the method and I'll try to work out the severity. So you've used a method that has gone from data to some claim, right? That's the nature of inference, right? And I want to know how well probed that inference is. So that's what I mean by you go to the second level. You give me the method, and then I'm going to do my work on it and see how capable your method was. And that goes beyond what you would do if you were just looking at the likelihood ratio. Because in order for me to understand the capabilities of your method, I have to go beyond the observed data and consider how your method would behave with other outcomes other than the one you observed under different hypotheses. Yes? It seems pretty obvious that we care about the general behavior of the method. That's just exactly what's denied by the likelihood principle. Does that help? Sorry, does that person want to follow up?
Yes, that helps. So then a method of inference, like for example, using Bayes factors. If you're going to quantify the severity of using Bayes factors for evidence, what would we plug into the severity function?
Okay, good. Let's say they would infer a Bayes factor of 10 or something, right? When one hypothesis is 10 times more likely than the other. I want to know the probability that they would give 10 of the Bayes factor to this hypothesis erroneously. Okay, I look at their method and they arrive at a certain Bayes factor or likelihood ratio, and I want to know what's the probability, what's the capability that that method could have avoided or enabled us to make wrong inferences. Now we saw with optional stopping, but the same thing happens with data dredging and so on, that we can be wrong with high probability if we allow those selection effects. Yes? That's where we disagree. Me and the Bayes factor person. Do you see what I'm saying?
I definitely see what you're saying. So final question. So computing the probability of getting a Bayes factor, say other than a Bayes factor of 10 if my model was wrong. How are we computing that probability? In the case of the parameters you're considering later on in your slides, we see that we are computing it based on the sampling distribution. So we can calculate severity of getting a mu 1 greater than 2, mu 1 greater than 3 from the sampling distribution. In the case of methods, how are we computing the probability?
Yes, it's the ordinary error probability, okay? Take the optional stopping. The same data dredged hypothesis can appear as one of the hypotheses in a Bayes factor. The fact that you can probably find some hypothesis or other that perfectly or well fits the data, okay, even if the claim is wrong, applies exactly the same way. Or consider the optional stopping. There's no disagreement about this point. If an experimenter uses optional stopping with probability 1, they will reject. This probability 1 is an error probability. Right? If they use this method, they will eventually, and this is a proper stopping rule, you can show it will stop in finitely many steps.
Yes, yes. Mm-hmm.
They will reject a sharp null, even though it's true. There's no disagreement there. But they say, nevertheless, it's irrelevant because that error probability is irrelevant to them.
Okay.
I guess that's as clear. Yeah, that's.
All right. Thank you. Yes. I appreciate your answer. Thank you.
Is there any question in the room? Go.
I don't know can you hear me? But should I go?
Do you hear,
Can you hear me?
Deborah?
Yes, I hear you.
Okay. So thanks for the talk. I'm curious, I'm not a Bayesian, but one thing that's sort of attractive to Bayesian analysis, I think, is that you end with so as long as you fix a prior, you sort of end with a posterior, which is like definitively this is what I think. And I think that's attractive to the wrong kind of the bad kind of cookbook significance testing, which is, I know at the end of the day, I know what I think. So the severity testing idea, I think is like sort of more how they ought to be, but there's a worry kind of like, when can I conclude that I am reasonably confident that this is severe enough? Like, do you have an idea of like when is the end of inquiry, as it were, or do you think this is up to context or like never-ending process?
No, these are great claims. First of all, with respect to the Bayesian, by and large, you will not get a posterior probability with the methods used. You'll get a Bayes factor, which is like a likelihood ratio. The reason that they use just a comparative support measure is it's really too hard to come up with an exhaustive set of hypotheses, which is what you would need for the Bayesian posterior. So they will usually give you like an odds ratio. This is the amount that you would increase the odds ratio given this data, and this way they don't have to deal with that. So don't forget that you don't usually get a posterior. But even if you do, the question is, what does it mean? I grant that I'm also giving a post data number, okay, in order to do better. And this post-data number is one that I think is altogether crucially important. How well probed, how well tested is your claim? I don't want to know how strongly you believe or how much you would have believed it more. And then with the conventional Bayesian, we're not sure how to interpret those. And those are really your main choices. There are sometimes frequentist priors, and then we can use them too. Okay, so you have to consider, this is a philosophical question of what is the meaning of the things that you're getting when you do get them? Usually just a comparison. If you do get a posterior, what does it mean? Okay. And why is it better than knowing? And by the way, I emphasize that we're not always in the context of severe testing. And that's why I think it's better not to try to conflate everything and reconcile. Say, yeah, sometimes I just want to know how strongly I should believe this or something, given I believe something else, or if I'm going to bet on something, right? But when we're talking about science, what we really want to know is how good a job you have done in ruling out mistakes. And I think it's this classic idea that Popper was onto with a degree of corroboration. It's just that he never fleshed it out.
Great, thanks.
Thank you. I have a question. So I want to ask something myself. Are these considerations about the role of probability in some sense dependent on the interpretation that we give to probability? Or it's simply the mathematical axiomatization, so the mathematical property or probability are relevant here. So it seemed to me at first glance that according whether we think probability in a frequentist way or in a logicist way, or etc., of course, can change something or not.
Yes, I absolutely agree that it's going to depend on how you interpret probability. Is it a degree of belief support, or is it something about long-run errors in applying the rule, or the frequency with which you will misinterpret data, or something rather different but related, this idea of capturing the capability of a method to probe for flaws. Now, I'm not saying that all error probabilities can be used this way. That's the reason that it comes under the performance requirement. But in certain cases, you can, and that's the philosophy of inference, of statistical inference that I've developed. Does that answer? I mean, I absolutely think that the interpretation is crucial. And you will be given computer packages and so on that won't tell you really what the probabilities mean. Well, they'll say you can change the default if you want.
Thank you.